Swayam Prabha. Digital India. Educated India.
In the previous lecture, we learned all about MOSFET devices. We started with a cross-section and we derived the MOSFET equations for different modes of operation. In this lecture, we are going to look at some second-order effects. For example, the body effect or channel length modulation effect or subthreshold region of operation. While we are doing this, we will be always comparing these MOSFETs to bipolar devices. In the previous lecture, we studied different modes of operation of the transistor, and we said that when VDS is equal to VGS minus VT, H, this is our VDSAT value for the transistor. If VDS is equal to VGS minus VTH, then the transistor, the channel under the gate goes into pinch-off mode, and it looks like this. So these are all the electrons which have been withdrawn from source, and exactly at where the drain is under the gate, we will say that the channel is pinched off when VDS is equal to VGS minus VTH. And if you remember, this is our channel length L. If we keep increasing VDS, the drain to source voltage beyond this value, when VDS is greater than VGS minus VTH, then what happens? I want you to think about it. So earlier we had a channel that looked like this, and then slowly it became like this. And you can probably extrapolate from this and say that as VDS goes beyond VGS minus VTH, the VDSAT value, then the channel kind of looks like this. As we said earlier, there is a reverse bias for the PN junction, which is drain to the substrate region or drain to bulk, and as a result of which we will have a depletion region over here around this. So the channel terminates just before the depletion region. The new channel length is then given by its L prime. So this is what we learned last time. Now the key point here is, as VDS keeps increasing beyond VGS minus VT, H, L prime will keep reducing. L prime will start moving in that direction slightly. It's pretty close to the channel length L, but it will start reducing somewhat. So we define delta L is equal to L, the design length, the design channel length, minus L prime. So we can say that this is delta L. And we can write a very simple expression which shows delta L divided by L is equal to lambda times VDS. And this is valid in saturation region. Lambda is an empirical parameter for the process. So percentage change in the channel length is equal to lambda times VDS. So if VDS goes up, then delta L will go up, as a result of which percentage change delta L by L will also go up. Now we can write an expression here, which is L prime divided by L is equal to L minus delta L divided by L, that is equal to, let's substitute back in here, this will give me 1 minus lambda times VDS. So we can say that L divided by L prime is equal to 1 plus lambda times VDS. The assumption is lambda VDS is much smaller than 1. So this is a second order effect. We can then say that 1 divided by L prime is equal to 1 divided by L multiplied by 1 plus lambda VDS. So this is the design length. When you design the transistors, that would be the channel length that we would start off with, and this is the actual channel length due to the VDS. Okay. If you remember the original saturation equation, let's write that again. Now this saturation region equation, you should commit to memory because we'll be using that over and over. IDS is given by half mu n Cox W by L prime VGS minus VTH. So in this case, L prime is the actual channel length. So we can rewrite this expression using this particular equation, half mu n Cox W divided by L VGS minus VTH square multiplied by 1 plus lambda VDS. And lambda is called channel length modulation coefficient. So let's gain some insights from here. What this is telling us is, if VDS increases, earlier there was no dependence on VDS in our saturation current of the transistor, and now we have a small dependence on VDS because lambda is also small. So if VDS increases, then the current IDS will increase slightly. So delta L by L again is lambda times VDS. So this is the relative variation in channel length. One more piece of insight here is delta L for a given transistor or a given process would stay about the same. So by increasing the channel length, we can reduce the percentage variation in the channel length, in the actual channel length. So for example, by if you increase L channel length, then automatically you would reduce lambda. That's the key insight I would like you to remember. So we use this quite a lot when we are designing circuits. For example, we would like our transistor to behave only like this. We don't want this effect. We want only this part of the equation. And the reason for that is this transistor, the current from drain to source does not have any dependence on VDS. So that makes it look like a constant current source, which is independent of the drain to source voltage. And constant current source has a lot of applications in circuit design, which we are going to go through in future lectures. But unfortunately, because of this channel length modulation effect, we don't get that. So as a designer, what we try to do is we try to keep the variation delta L by L in control by increasing the channel length of our transistors. So if you use larger channel length, then delta L, as I said, for a given transistor or a process is about the same. So if I increase channel length, then the lambda would be smaller for a given VDS. So we use longer L, longer channel length device, that would give us smaller lambda. Let's plot this, and we will try to draw the similarities between what we have learned earlier also about the bipolar transistor. So this was our transistor characteristics, IDS, and on this axis is VDS. And we said that our original device, this is the inverse parabola effect. And if the channel length modulation, these are different VGS minus VT numbers. So this would be VGS3 minus VTH, the VDSAT number. From the first order equations, we saw that the current does not change, and this is the way it looked like. It looked flat. The current values did not have any dependence, and these are for different VGS1, VGS2, VGS3, all greater than VTH, threshold voltage. Now we have the effect 1 plus lambda VDS. That's the multiplier we talked about for this saturation region. What you will see is, you will see increase in the, since over here the VDS is increasing, we would see increase in the current because of this multiplier 1 plus lambda VDS. So what you will see in the transistor characteristics is something that looks like this. So the actual transistor curve is going to look like this with channel length modulation effect, something like this. And the reason I have drawn these dotted lines is, if you hypothetically extend this line, which is telling you that this number will go to 0 when VDS is equal to minus 1 over lambda. Okay, so this would be your minus 1 over lambda. This voltage correlates with, we learned something like this in bipolar case, which is the early effect, or we also call it here early voltage. Lambda is again process technology dependent parameter. For example, you may get your transistor designed either in UMC or TSMC or SCL or a global foundry, different foundries, and each one of them will have, transistors will have a different lambda value for a given process. So as a designer, when you are in the design phase, you need to know all these numbers. In this class, you are going to learn mainly how do you analyze different circuits. So the impact for you is, for a given circuit, you need to figure out why do you use larger channel length devices for this particular application. This is the reason. If you want to reduce the dependence on the drain to source voltage and you would like to get an ideal current type of effect, then you would like to make sure that you use larger channel length, because larger channel length would definitely mean the lambda will be smaller. Now we will study body effect. Let's draw the transistor profile one more time. As I said again, you have to get used to drawing the profile of the MOSFETs, of course, and bipolars too. Let me explain body effect to you. If you look at this transistor, you will see from gate to substrate, it looks like two capacitors which are in series. This would be your substrate connection and this would be your gate connection, and in between you have the channel. In earlier example, we had source and bulk. Both these terminals were connected together to ground. Something interesting happens when you change just the bulk terminal, or if you introduce a voltage difference between source to bulk. If you introduce a voltage between these two, then what happens is what I'm going to explain to you. Let's look at our rudimentary picture that I'm showing you here as a cap divider, capacitor divider. For a given substrate potential, let's say it was connected to ground, then I needed to put in some VTH value over here to get a channel going. The inversion layer is formed when you have certain voltage, VTH, threshold voltage applied to the gate, between gate and the source. Intuitively, if I take this substrate potential, if I take it negative, take it down below ground or whatever this value is, what do you expect that you should apply to the gate to form the channel under the device? So if you look at this analogy, then you can convince yourself that, of course, if the substrate potential goes down, then I need to increase the gate voltage further to get a channel formed under the gate. And this is exactly what happens. So intuitively speaking, if substrate V sub is reduced compared to V source, then VTH required will increase. The voltage that you need to apply to the gate will increase. And this effect is called body effect. The reason it's called body effect is because you're changing the voltage of the bulk region or body region of the transistor. I have not shown you how to draw the symbol for the transistor, but now we will draw the symbol so that things will be clearer. The NMOS transistor is drawn this way. This is our gate region. This is the drain region, and this is the source. And the bulk is, or the body is shown separately like this, generally the center. So this would be your body connection. And we can draw different voltage sources to keep things general. Let's say there is a VG applied, and let's say there is a VD applied, and we say there is a VS applied to make it more general, and there is a VB applied. So what body effect is telling us is, if I decrease this bulk voltage below the source voltage, Vs, then the threshold of the transistor will increase. In other words, we can say if VSB is increased, then we require higher VGS is required to invert the channel. And this is telling you that the threshold voltage of the device has gone up because of this effect. So let's write how this body effect is represented. VTH is given by VTH0 plus gamma square root of 2 phi f plus VSB mod of that minus 2 phi f. Here VTH0 is when VSB is equal to 0. Gamma is a body effect coefficient, is given by square root of 2q epsilon Si n sub divided by Cox. So gamma is a technology dependent parameter, and it ranges from 0.3 to 0.4 volts, square root of that. That's the unit. Another interesting observation, then you could say that, hey, you're telling me that if I reduce bulk potential compared to the source, compared to the source potential, then my VTH increases. Then I could go the other way around also, right? I can increase the bulk potential compared to the source voltage, which is right here. And in this particular equation, you can see that this number will become smaller than this number, and we will see a negative sign over here. And yes, the threshold voltage will reduce. The reverse effect is also true. If you take the bulk potential higher than source potential, then you will see a reduction in the threshold voltage. I have myself used this effect in some of my designs. One caution though I would like to make sure is, whenever you do something like this, you should always look at the transistor cross section and see what's happening. You cannot just take voltages and move them around and expect the transistor to work. So for example, in this particular case, let's imagine this scenario, and I'm just trying to teach you a technique where you can yourself make a decision. So for example, if I make this bulk potential positive compared to source potential, what will happen? You can quickly see that we have a P plus and here is a N plus. So there is a diode between bulk to source. And if I take bulk positive compared to the source, then this particular diode will get, if I'm taking this positive, you can see that the diode will get forward biased and you will start seeing current which is a large current because of the forward biasing of the diode. This is definitely not desirable because this is current which is wasted and your transistor equations will change because you have not taken that into account. Just for the purpose of reducing the threshold voltage, you can use it. What I like to do is I like to put in some resistor in this path so that we can limit the current which is going to flow in this direction. Okay, so we can limit this forward biasing of the p-n junction to that current to be a very small value. Next, we are going to look at subthreshold region or subthreshold conduction of MOSFET transistor. Before we get into that, what I would like you to do as an exercise is the following. Let's assume the transistor is in saturation region. And this can be very well be an interview question for you. So I would really like to try to answer this question on your own. And you will see quickly why this is an important question. Okay, so what I'm asking you to do is once I describe the question, you can pause the video and try to answer the question yourself. What I have given you is, I have told you that the transistor is in saturation region. Under that condition, what I would like you to do is plot this particular graph. On the x-axis, I'm plotting VGS, and on the y-axis, I'm asking you to plot square root of IDS. You can pause the video now and try to attempt it on your own. The clue is the transistor is in the saturation region. So from the first order, if you remember, IDS is equal to mu n Cox W by L divided by 2 VGS minus VTH square. I have told you that the transistor is in saturation. So when VGS is equal to VTH, let's write, before we get there, let's write the square root equation, which is square root of IDS is equal to square root of, let's say this is constant, VGS minus VTH. If you look at this particular expression, then you will quickly say that if VGS is equal to VTH, then square root of IDS should be 0. And that's exactly what we would expect here. So this would be, let's say, our VTH. And then what is the nature of this curve? Nature of this curve is it should be linear. So at VGS is equal to VTH, the IDS should be 0, and then it should be 0 like this. And then you would expect the current to linearly go up like this. Okay, and the slope of this will be square root of mu n Cox W by L divided by 2, square root of the whole thing. So this is what we gather from the model that we have for the saturation region. What we are saying here is at exactly VGS is equal to VTH, the current IDS is equal to 0. And then it starts flowing after VGS increases beyond VTH. And for VGS is less than VTH, the current is 0. So this expression is kind of telling you that, hey, there is a discontinuity here. Okay, the current is either 0 or it's increasing. But we know that in real world there are no discontinuities, right? So there is always some current flowing, small amount of current flowing while we are in this region. And if you have to plot the real curve, it looks kind of like this. I have exaggerated it quite a lot. So this region of operation is called sub-threshold region. We also call it weak inversion region. VGS is less than VTH. There is some finite IDS, however small, it will flow. And it has exponential dependence on VGS. And if you want the exact expression, the IDS in this region is given by IDS is equal to I0 exponential VGS divided by eta VT. Thing to note here is we see VT here, which is KT over Q, and eta is greater than 1. This is again process dependent parameter that you'll get. So quickly you can see that, hey, this expression, I have seen it before. This expression represents our bipolar friend. In this region, subthreshold region, the MOSFET actually starts behaving like a bipolar transistor. However, we have this eta which is greater than 1. Interesting point about this operation in subthreshold region is we are talking about really small currents over here. Okay, so we are operating the transistor in extremely low current region. So naturally, this mode of operation is very low power. And many of the Swiss watches, they exploit this region of operation for the transistors in that region. So just to keep that in mind. Now, as a rule of thumb type of designer, we really, as analog designers, we like to stay away from this region. Why? Because it's not very well modeled many times, and we are trying to keep the transistor in saturation region. So we try to stay away from this region, and what I mean by that is we try to keep our device operation a little bit away from this region. So for example, I would rather operate here in saturation region than anywhere close to this region, the VTH, close to VTH. So what we say is we like to design our circuits with this to be, let's say, 100 to 200 millivolts away. So you would like to use your transistor, you would bias the transistor VGS 100 to 200 millivolts away from the VTH. What does that mean for a saturated transistor? What that is telling you is VGS minus VTH, we would like it to be greater than, let's say, 100 to 200 millivolts. So this is like a margin that we would like to keep. And we already know what is VGS minus VTH. For a device, it's called VDSAT. So we would design the transistor with VDSAT values which are greater than this value. Another insight here, as I would like to show you, is if VDSAT gets close to 0, that means your VGS is coming close to VTH. Okay, so you are coming close to this, this part of the curve. So we want to keep VGS minus VTH, which is the VDSAT of the transistor. We would like it to be more than 100 millivolts at least to keep away from this region. Thank you.